Hi, we've done a number of videos on solar power, and I am continually doing experiments trying to improve the performance of commercial solar panels and solar cells. This is one of those experiments, and the results are pretty exciting. Solar power is a multi-billion-dollar, billion-watt industry, and slowly the manufacturers are improving the performance of solar panels and solar cells with better engineering and better chemistry. But there is a fundamental limit on the performance of solar cells, and it's unavoidable: heat. The way a solar cell is manufactured is they take a substrate, aluminum or plastic, and they will deposit on it a thin layer of silicon that is doped with a different atom, like aluminum or boron. Then they'll deposit a second layer of silicon that is doped with a different atom, like phosphorus. Because of the different atoms present in the layers, at the junction of the semiconductor, a small electromagnetic field or potential is created. So when a photon comes in from the sun and strikes the silicon, it can kick loose an electron, and that field will urge that electron away from the depletion zone at the junction and send it to the conductors that lead it out as electricity. Now, the solar silicon will respond to wavelengths between about 400 nanometers in the blue out to about 1,000 to 1,100 nanometers in the near IR. But the solar spectrum is much broader than that, and any of the heat or light that is absorbed by the panel but not converted into electricity is converted into heat. In addition, that process I told you about is not 100% efficient. Some of those electrons don't make their way out and fall back into the depletion zone, creating more heat. And that process is thermally dependent. As the temperature of the junction rises, the heat causes the vibrations in the atoms to increase, and it makes it harder for the electron to make its way out of the junction and into the conductors. So solar cells become less efficient as they become hot. And it's not just when they get really hot, they start to become inefficient. It's a progressive process all the way from the highest temperature that the solar panel can tolerate, all the way down far below zero. That's why solar cells are more efficient in the winter than they are in the summer. The reason they don't seem to be is because the sun is hitting at a more oblique angle, and you're getting fewer photons. But the photons that do strike the panel are more efficiently converted into electricity. Therefore, when you are engineering or building a solar cell array, you want to do everything you can to passively keep it cool. For example, if you mount it on your roof and you paint or coat the roof with a highly reflective paint or coating that sends most of the solar heat away, you don't create large clouds of hot air that waft around the array that's sitting on top of the roof. If you take the panels themselves and mount them, you want to mount them in such a way that you have a lot of free airspace around the panel so that you get convective cooling, because the panel, when it's operating, is always going to be at a higher temperature than the surrounding air. What we're doing in this experiment is testing whether or not active cooling can lower the temperature of the junction sufficiently to boost the efficiency of the whole apparatus enough that we can more than drive the cooling system and get some net benefit out. To do that, I took one of these solar panels we obtained last year on Amazon from a company called Weize, W-E-I-Z-E. They're pretty nice panels. They're sold in pairs at $170 a pair, and each panel is rated at 100 watts. That's at noon on the equator. Here in New England, 60 to 70 watts is more typical. What's nice about the panels is they have a stamped aluminum frame around the outside that gives it rigidity and mounting points, but it also creates a space between the panel and the edge of the frame that we can use to build an air duct, and that's what I did. Now, on the back of the panel we're going to be testing, I took a 1 millimeter thick sheet of aluminum and attached it to the sides and left a small gap at the top and a large gap at the bottom. They're farther from the fans. And the combined area of those two gaps is equal to the combined area of the 3 ventilating fans. The fans are pretty impressive. They're from a company called Orion, and they are 12-volt DC wash-down fans. So you can spray them with a hose, it can rain on them, they're perfectly fine. And they're very efficient. When run at 12 volts, each fan will consume 5 watts and produce 120 cubic feet per minute of airflow. That's each. However, as you lower the voltage, the power consumption drops more quickly than the flow. When you bring the voltage down to 6 volts, which is the sweet spot, each of the fans will draw approximately 1 watt, but still move 60 cubic feet per minute. So when we set this thing up and tested it, we found that the results were a little equivocal, not that impressive. The problem was that the surface area on the back of the panel wasn't sufficient to interact with that airflow. We needed more surface area. To do that, I put these fins on the back surface to increase that surface area. Now, if I was to use a commercial heat sink or heat spreader like this, we would triple the cost and the weight of each of the panels, so I decided to make it myself. I took the same 1 millimeter thick sheet aluminum, and I have a friend that has access to a sheet metal shear and a press brake. And so I trimmed out a whole bunch of strips and then put them in the brake and bent them into these right angle shapes like this, 2 centimeters by 3 centimeters, 2 by 3. And the first couple took me about 10 minutes to kind of figure everything out. But once I got rolling, I could make 2 or 3 very long strips per minute, made over 100 in 1 hour. Now, if you don't have access to that kind of equipment, you can find a local job shop or a machinist that will do this for you. You'll pay more than just the stock aluminum, but they're probably better at it than you, so they could probably produce even more of these pieces of metal. And it's certainly going to be a heck of a lot cheaper than doing something like this. We then applied those strips to the back of the panel using some of our thermal epoxy and then retested it. Now, you might notice this articulating frame that I have here. This was built for tracking experiments for solar panels and other things. We'll get into that later. But in this case, we're going to be operating it manually, and the purpose of this is to keep the panel aiming directly at the sun. You want a normal or a perpendicular from its surface to be directed directly at the disk of the sun, so we don't get any foreshortening during the few minutes during the test that the sun is moving across the sky. I'll show you the little technique that I use to do that, but every couple of minutes I'm going to be tweaking the panels 1/4 degree or so to keep things bullseyed on the sun. Now, the instrumentation we're using includes a thermometer over here. See if it's on. Yeah. And the number in the lower corner represents the temperature of the box. That we really don't care about because it's baking in the sun. The larger number up here is being fed from the thermocouple that has been glued to the back surface of the panel. So it's the panel temperature. That's the number we care about. This is the power meter. The power is fed from the panels into this meter, and it will read volts, amps, and in this lower corner down here, the combined product, watts. That's the other number that we're going to care about. The power is then led out of the meter into a resistor array that provides the load. I did some experimenting and discovered that these panels are pretty forgiving. They will produce near peak output over a fairly broad load range, but it peaks around 7 ohms. So I took 7 1-ohm ceramic resistors, wired them up in series to produce a 7-ohm load, and then put the whole thing down in a bucket of water to act as the heat sink. It works well. You might wonder why we're not using a charge controller, sort of an adaptive controller. Because one of those controllers, by adapting the resistance perfectly for conditions, could probably tweak another watt or 2 out of the panel. The problem is the algorithms, what drives the function of the machine, is not accessible to us. It's sort of black box. So if it's making changes in the load, it may interfere with the results. And because we're doing a comparative test, this panel, same conditions, just a change in temperature. This does a very good job of doing that comparison without adding an additional unknown of the charge controller. This is the power supply that drives the fans. In theory, DC fans, DC output from the panel, we could drive the fans directly from the panel. But this allows us to adjust the voltage perfectly for what the fans need, as well as dissects out the amount of power that the fans are consuming relative to the amount of power change we're getting in the panel due to temperature. Now, let me come around here and show you the last thing. I have this reflective insulator put in front of the panel so that while we set up and while I was talking to you, we didn't heat soak the panel and start it at an elevated temperature. And then when I take this off, we're going to note the temperature. Let me turn this back on because it's got an auto shut off here, which is 19.3 degrees. And we'll notice the initial power when the panel is as cool as we can get it at starting ambient temperature. This is the alignment technique. I have a machinist's square. I place it on the front of the panel or on the insulator, which is lined up with the panel. And as I move this back and forth in the sun, you can see the shadow is moving past the vertical. And if I move it up, it does the same thing, and down the same thing. When I line everything perfectly, this shadow will disappear because it lines up with the vertical, like that. That is the starting position, and that's where we're going to begin the test. And that's what I'm going to be doing every couple of minutes, just to make sure we stay perfectly aligned. So when I pull this off on 3, let's notice the power output with the cool panel. 1, 2, 3. Get my head out of the way. And what do we got? 68.8 watts. And you'll notice the temperature is already fairly rapidly rising. There are panels out there that attempt to do something relatively similar. They're called photovoltaic thermal panels. And they use a whole series of tubes on the back of the panel to circulate water to carry away the heat. And there are some DIY channels that have done something similar where they put drip tubes across the top of the panel and actually flow water over the panel. They're waterproof, they can be rained on, it's perfectly fine, and it has the added advantage of keeping the panel perfectly clean and free of debris. We decided not to do it for this reason. Water is an excellent heat conductor, but itself, it's not a heat sink. And so if we don't have some way of dumping the heat, the water will just continue to rise in temperature until eventually it gets to the same temperature of the panel and doesn't do any cooling. We need to dump that heat. And so if we dump that heat with a water-to-air heat exchanger like a car radiator, we not only have the power requirements of driving the fans that do the exchange as well as the water pumps that move the water, potentially lowering the overall efficiency. If you were lucky, and you had a lake or an artesian well next to you and you could use that instead of the heat exchanger. The problem you get to there is it's at a fixed temperature, which obviously has got to be above freezing. And so if you start circulating that water from that source, eventually when the air temperature drops below freezing and continues to drop, it will actually act to warm the panels and lower the efficiency. So we decided to stick with a simpler, leak-free system that potentially is more efficient. Now if we look over here, just before we start letting this heat soak, you can see that we've gained about 7 degrees and we have dropped about 2 watts. We're going to give this a little while to equilibrate and we see where we get to once this thing heats up. Okay, you can see that the temperature has risen to almost 53 degrees and the power has dropped to 58.7 watts from 68.8 watts. So we've basically lost 10 watts of power and we have risen about, 34 degrees, something like that. Now I'm going to turn on the fan and we're going to see what happens. Okay, 6 volts. Fan coming on. Okay, and you can see that the temperature is already starting to drop. Let's give this another few minutes to equilibrate and see where we get to. All right, we've given this a few minutes to equilibrate, and you can see that we've dropped the temperature down from about 53 degrees to about 39 degrees, and we have increased the power from 58.8 watts to about 63.4.6 watts. So we've gained about 5.5 watts for an investment of about 3 watts in power. Pretty significant improvement in the performance of the panels by simply using the fans. It really does work. You can actually get more power out than you put in. I like that. The problem is the engineer is going to say something else. They're going to say, well, for this modest power gain, is it worth it? Does it make sense? Is it worth doing? And I think it is. The first argument is panel longevity. Solar panels degrade over time. Some of that is due to humidity, some of it's due to just the photons hitting the surface. But the biggest killer is heat, the number of hours spent at any given temperature. And it isn't linear. If you're running a panel temperature of 50 to 60 degrees, the degradation rate is about 0.5% per year. If you go to about 80 degrees Celsius, the rate increases to about 1% per year. And if it gets to about 95 degrees Celsius, it jumps to about 2 or 3% per year. That's a fairly significant increase. Now, as you can imagine, if you were to install, say, a $20,000 system on your roof that was designed to last for, say, 25 years, and you could get 5 or 10 more years of life out of the system, that may more than justify the purpose of putting in the fan system. However, you might argue that, all right, the $20,000 isn't just paying for the panels. It is paying for the panels, but also the installation costs and the replacement costs. And the real cost of your system is probably not as low as $20,000. If your neighbor's taxes are being used to subsidize your panels, you're paying more because your taxes are being used to subsidize their panels. In addition, these things contain heavy metals. And so when you dispose of them, it's not free. The second argument is we are actually making more power. And that improvement in power means you could either run your toaster more often, you could run your air conditioner more frequently, or you could buy a slightly smaller system and get the same amount of power out. And this test is an extremely conservative test. Here in New England, we don't get a very high photon flux, 60, 70 watts out of a 100 watt panel. But in areas of the world where solar power makes more sense, Southwest US, the Mediterranean, Australia, in those conditions, the panel temperatures are running much higher than this, 20, 30, 40 degrees Celsius higher. And even though the air temperatures there are higher, they're not 20, 30, 40 degrees Celsius higher. If they were, in some of those areas, you'd be dead. So with a higher temperature differential between the panel and the air, the same fan system will carry away more heat. And so there will be a larger differential between a passively cooled panel and an actively cooled panel. And the final argument is that if I was going to install these things on my roof, put 40 of these panels up there, I wouldn't install 120 of these tiny fans. And as fans increase in size, they increase in efficiency. So if I double the diameter of one of these fans, I'll get 4 times the airflow, but maybe only invest 3 times as much electrical current. The point being that a smaller number of more efficient fans is easier and it's more efficient. So it's kind of a good deal. You could even potentially use a number of large blowers to ventilate multiple larger units, making it even easier to do. So with all those arguments, you might say, well, if it's a good idea, why isn't anybody doing it? Point is, somebody is. There is a company out of Australia called Sunovate, which is doing exactly this. They use a slightly different design in the cooling system, but they're doing direct air cooling. And they even tout in their literature that if you're doing a big industrial setup, you could use some of that waste industrial heat for other purposes, drying wood, making paper. But even if you just dumped it into the atmosphere, it still makes sense. So we wish them luck and any other companies that decide to add this as a feature to their existing panels. But as I've shown you, it works. It's not difficult to do. You could do it yourself. So hopefully you found this interesting and potentially maybe even useful. And if you like the kind of stuff that we're doing on this channel, please take a second and look at some of our other videos. We've done some pretty interesting things. And if you're willing to, please subscribe, because if you do, it helps the channel to grow, and the bigger we get, the more we can afford to do, both the equipment that we buy and the labor that we use to produce the videos. In any case, I want to thank you for watching. You have a wonderful afternoon, and we'll see you soon.